All right, welcome back. Today we're going to talk a little bit about the Bohr model, and we're going to do a demonstration on how to create the Bohr model for the first 20 elements on the periodic table. The reason why this video is going to focus on the first 20 is because after calcium, which is element number 20, you really need the quantum mechanical model to describe the positions of the electrons in the atom. But for the first 20, this technique will work just fine. And it really does work for all of the elements, but it's easiest to describe without the quantum mechanical model for the first 20. So let's get started. The first thing that you need to know when making the Bohr model is the period number. You can find the period numbers along the sides of your periodic table. Those are going to be the horizontal rows. So you can see them listed here along the side. So there's 7 periods on the periodic table. This is going to correspond to how many rings that you need. So the period number tells you two things. One, it tells you the required number of energy shells. Then it also tells you which shell is going to be the valence shell. For example, if we're looking at oxygen. Oxygen is in period 2. So therefore, it's going to have 2 energy shells, and the second shell is going to be the valence shell. If we're looking at calcium, on the other hand, calcium is in period 4. So therefore, it's going to have 4 energy shells, and it's going to have the 4th shell as the valence shell, which is the outermost shell. Okay, so that's the first thing that you need to know. The second thing that you need to know is the group number, which are the vertical columns. So the group number tells you a couple things. First of all, it's going to tell you for the main group elements is how many valence electrons there are in the atom. When you're looking at the main group elements, which are groups 1, 2, 3, 4, 5, 6, 7, 8, these numbers tell you how many valence electrons will be present in the atom. So for example, if we're looking at, say, fluorine. Fluorine is in group 7. Right? Since it's in group 7, that means that fluorine is going to have 7 valence electrons. If we're looking at group 2 is going to have 2 valence electrons. The same holds true for anything that's labeled A, which are the main group elements. Now, the way that you think of the periodic table and building the Bohr model, think of the periodic table as an apartment building, right? The only way you can build something on the 4th floor, for example, or in the 4th period, you have to build the first 3 rows before it. You can't just go and build the roof of an apartment building or the roof of a house without building the 1st floor, the 2nd floor, the 3rd floor, so on and so forth. Okay? And then you think of the group numbers, so that's how you think of the period numbers. Think of those as floors. You think of the group numbers as rooms on each floor. So for example, on the 1st period, you're going to have, or the 1st floor, you're going to have 2 rooms on that floor. Hydrogen and helium. So therefore, your first energy shell can only have 2 electrons in it. If you're looking at the 2nd period, then you can only have 8 electrons in the 2nd period. 1, 2, 3, 4, 5, 6, 7, 8. So on the 2nd floor, you can have a maximum of 8 rooms or 8 elements. Therefore, your second energy shell can only have a maximum of 8 electrons. And lastly, if you're looking at the third row, you can also have 8 electrons. But the third floor can have a maximum of 18. But that, of course, is if you extend past the first 20 elements, which we're not going to do in this video. Okay, so let's put it all together. All right, so let's say, for example, we're looking at magnesium atom. The very first thing that we have to do is we have to find magnesium on the periodic table. Magnesium is in period 3, and it's going to be in group 2. So we know that since it's in period 3, it's going to have 3 energy shells. Because it's in group 2, that means it's going to have 2 valence electrons. So now, only thing that we have to do is we have to draw the Bohr model. Okay, so very simply put, first thing that you have to do is you have to draw the nucleus. Nucleus is going to be the center of the atom. And of course, the nucleus is going to contain the protons, which in this case, there's 12 protons in the nucleus, as well as some neutrons, but we don't know based off the information that we're given. Now we're going to draw our first energy shell. Just a simple circle around the nucleus. So the first energy shell is going to coordinate with the first period. So inside of the first period, we have 2 elements, hydrogen and helium. So therefore, since we passed the first period, we have to have 2 electrons in the first period. 1 from hydrogen, 1 from helium. Because there's no more elements in the first period, it's time to move on to the second period. So our second period. How many atoms do we have in the second period? Well, let's count. We have 1, 2, 3, 4, 5, 6, 7, 8. So therefore, we need 8 electrons in the second period. 1, 2, 3, 4, 5, 6, 7, 8. Now, in this case, we have them paired up. Okay, in the first energy shell, they're not paired. In the second energy shell, they are paired. Reason being, because in the first energy shell, the electrons travel in opposite directions. In the second energy shell, the electrons also travel in opposite directions, but they travel in pairs. Okay, so if you have 8, or I should say if you have 4 or more, they should be paired up. The first 4, you want to draw it northeast, southwest is how I think of it. So you draw your first one here. That'll be the first one. And then once you have more than 4, you'll start to pair it up. Okay. So now we're done with the second energy shell. We have to move on to the third energy shell. So how many atoms did we go into the third period? Well, we traveled past sodium and we traveled to magnesium. So therefore, we need 2 electrons on the outermost shell. So now you can see that in our first energy shell, E1, we had 2 electrons. Energy level 2, we had 8 electrons. And energy level 3, which happens to be our valence shell, we have 2 electrons. And this whole shell is our valence shell. So that's the Bohr model for magnesium. It indicates all of the electrons in the atom and the locations of the electrons. Pretty easy. Okay. So let's take a look at another example. Let's do silicon. So let's find silicon on the periodic table. All right, so silicon just so happens to be in the third energy shell as well, this time in group 4. So I'll put a box around silicon here. Okay, so we know that silicon is going to need 3 energy shells. This time it's going to have 4 valence electrons in the outer shell. That's because it's in the third period. It's going to have 4 valence electrons because it's in the 4th group. Okay, so now we can simply draw our Bohr model. So we have in the nucleus, we're going to have 14 protons because of the atomic number of 14. Then we have to build from the first floor up to the 3rd floor. So on the first floor, we have 2 electrons. On the 2nd floor, we're going to have 8 electrons from the 8 elements present here. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. Notice, as I mentioned before, the first 4 electrons are unpaired. Then as we get more than 4, we start to pair them up. 4, 5, 6, 7, 8. So now the second row is complete. Now we have to look at the 3rd row. So now, how many elements do we have to travel in the 3rd period to reach silicon? Well, 1, 2, 3, 4. So therefore we need 4 electrons in the outermost shell, as also indicated by the group number. Here's our Bohr model for silicon. So in our first energy shell, we have 2 electrons. Our second energy shell, we have 8 electrons. And our third energy shell, we have 4 electrons. So that's the Bohr model for silicon. Okay, so anytime you're doing the Bohr models for atoms, that's where you have equal amounts of protons and electrons, the process is going to be the same as the previous 2 examples. However, we do have the option of making Bohr models for cations and anions, which we're about to do right now. Just as a refresher, cations are positively charged atoms. In order to form cations, we have to subtract valence electrons. Also, when we subtract the valence electrons, the valence shell will also quote-unquote disappear. And that's because the electrons themselves carve out the shape of the orbital. If there's no electrons present in that orbital or energy shell, the energy shell won't be present. And these are generally formed by metals. Anions, on the other hand, are negatively charged. You have to add valence electrons. And these are generally formed by nonmetals. All right, so one last thing that I want to mention about cations and anions are how they're named. Cations are named simply by taking the element name and you're going to add ion to it. So for example, calcium, when it's ionized, it becomes a calcium ion. Okay, so we simply took the element name and added ion to it. Okay, so that's for cations. For anions, a little bit different. You're going to take the element root, and you're going to add the suffix plus ion. Okay, so for example, nitrogen. We drop the ending, which is in this case O-gen. We keep the NITR. We're going to add IDE as a suffix, and then we're going to have ion. So now, nitrogen, when it ionizes, becomes nitride ion. Okay? So, one last thing that you need to know about cations and anions, and that's mostly from the periodic table. So, group 1, 2, and 3, these are going to be your cations as far as the main group elements go. Of course, all of your transition metals will also form cations because they're metals, but in this case, we're just talking about the main group elements. Now, what you should know is that group 1 is going to form a 1 positive cation. Okay, so the charge of any ion coming from group 1 will be 1 positive. The charge of any cation coming from group 2 is 2 positive. Coming from group 3 is 3 positive. Okay? That's because they lose 1 electron, 2 electrons, and 3 electrons respectively. Now, for groups 5, 6, and 7, these will form your anions. Okay? So, group 5 forms a 3 negative charge. Group 6 forms a 2 negative charge. Group 7 forms a negative charge. Okay, when they form ions. That's because their goal is to get to a total of 8 valence electrons. Cations lose a certain amount of electrons to get to the previous noble gas configuration. Okay? So, this is a summary of everything that you need to know about cations and anions, and this information is going to be most helpful when you're forming the Bohr model of cations and anions. Okay, let's do an example for cations. Let's start with a potassium ion. So, we know that potassium, if we look on our periodic table, we know that potassium is in period 4, it's in group 1, and we know that it has 19 protons. You're going to need 4 energy shells because of the 4th period. It's going to have 1 valence electron because it's in group 1, but because we're talking about an ion, we also have to lose 1 valence electron, which then in turn means that we're going to lose the valence shell. Okay, so what it turns out to be is we'll wind up having 3 energy shells, and the valence electrons will change. So let's draw it together. All right, so we're going to start with our nucleus. Potassium, as mentioned before, has 19 protons. Okay, the first energy shell, as always, except for hydrogen, will have 2 electrons. That's because there's 2 elements in the first period. The second shell has 8. Now, the third shell, in this case, also has 8. Now, we're on to the 4th shell. So, we know that potassium normally has 1 electron in the first shell, or in the 4th shell, I should say. But in this case, we're going to remove that electron, and we have to go back to the previous configuration of the previous element. So instead of being potassium here, it's going to wind up looking like argon because we lost our valence shell and we have to move back a row. So now we have to have in our valence shell 8 electrons. That's what we have here. And now we're taken care of. We don't need to draw the 4th energy shell because there's no electrons present in that shell. The only thing that we need to add now is the charge of this ion, which in this case, it's positive. Okay, so let's count up how many electrons we have just to make sure. So we have energy level 1 equals 2 electrons. Energy level 2 has 8 electrons. Energy level 3 has 8 electrons. And this one turns out to be the valence shell now. Now, you might be thinking to yourself, oh, wait a minute. How is it that if we remove electrons, we have a positive charge? Well, there's a couple ways I want you to think about it. And you decide which one is best for you. Okay? So, myself, I'm a numbers person. So, if we have 19 positive charges and we add 18 negative charges, you're going to wind up with a sum of 1 positive. So it's simple algebra. If you understand it mathematically, this is the mathematical explanation. Now, some people are visual. So here's a visual explanation. For example, a seesaw. One side is positive, so it contains the protons. One side is negative. Let's say, for example, if we had 18 electrons, and if we draw 19 protons. So now we have 18 electrons and 19 protons. So now you know that a positive charge and a negative charge will cancel each other out. So if we go through and we cancel each positive charge out with a negative charge, let's see what we have left over. We have 1 positive charge remaining. So this is how we come up with the 1 positive charge. So whichever method works easier for you, if you think of it visually or if you think of it mathematically, both explains why we have a positive charge on a cation, because essentially we have an unpaired proton. Let's do another one for a cation. Let's look at an aluminum ion. We know that it's in group 3, so it means it's going to lose 3 valence electrons, and it's going to have 13 protons. Aluminum is in the 3rd period. Our nucleus, 13 protons. Our first energy shell has 2 electrons in it, separate from one another. Second energy cell has 8 electrons. Now, when we look at our 3rd shell, it should have 1, 2, 3 electrons, but we lost those 3 electrons to form a 3 positive charge. So 1 positive, 2 positive, 3 positive. So now, this is it. So now we just have to label the charge of this. Because we lost 3 electrons, it's going to have a 3 positive charge. And now, that's it. So let's label our shells. Energy level 1, we have 2 electrons. Energy level 2, we have 8 electrons. So this time we have a fluoride ion, not to be confused with Flo Rida, the rapper. All right? So, fluoride, you notice it has the IDE at the end. So you won't find an IDE on a periodic table. You have to look for the root word. But in this case, IDE will always signify an anion, okay? So, when we're looking at our periodic table, we see lots of elements, but there's only one that has the root of fluor, and that's going to be fluorine. as it turns out. Fluorine has 9 protons, and it's going to form a 1 negative charge because it's in group 7. In this case, we're going to add 1 valence electron to the valence shell. So in this case, the valence shell is in period 2. So that means that the second energy shell is going to be the valence shell. In our nucleus, we're going to have 9 protons. We pass the first energy level, which has 2 electrons in it. Now we're on to the second energy level. We have 1, 2, 3, 4, 5, 6, 7 normally, but we know that we're looking for fluoride ion, so therefore it has to have a negative charge, and that means we need to add 1 more electron to it. So now it's going to have a similar configuration to neon, but it has a different amount of protons. The protons makes the element different from one another. So now this is our Bohr model for a fluoride ion. Very simple. We just added the appropriate amount of valence electrons to the valence shell. So let's count them up. Energy level 1, we have 2 electrons. Energy level 2, we have 8 electrons. Visually, if you need the visual explanation, which is fine, think of the seesaw where we have positive protons over here, negative electrons over here. Draw our boxes. Then we'll cancel them out. 9 on this side. 9 on this side. So now you're left with a 1 negative charge on the electron side. So it gives you a negative charge. Okay, so let's take one last look at phosphorus. So a phosphide ion. Okay, so phosphide ion. So we know that the IDE makes it negative, so we have to look for the root phosp. So when we look on the periodic table, we're going to find phosphorus in group 3. So that means that we need to add 3 valence electrons to the third energy shell to make it an ion. Let's set this up. We have 15 protons in our nucleus in this case. Okay, as always, we need to count our shells. So the first shell has 2 electrons. Our second shell will have 1, 2, 3, 4, 5, 6, 7, 8 electrons. Now our third shell will have, normally has 1, 2, 3, 4, 5. But we need to add 3 more, 6, 7, 8. So our third shell will have 8 electrons total. So it gives it a 3 negative charge. Let's make sure that we label our shells. I kind of jumped ahead of ourselves here. That's okay. Energy level 1 has 2 electrons. Energy level 2 has 8 electrons. Energy level 3 also has 8 electrons, and this is our valence shell. Okay, so that's all I have for you today. Hopefully this video was helpful. If it was, please like, share, and subscribe. And join us next time. All right, thanks a lot.